Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 17 on the indefinite integral.
Welcome to Chapter 3, on integration. In this chapter, we're going to take what we've learned about differentiation and run it in reverse. In today's lesson, we'll begin with an introduction to the indefinite integral and see its applications and motivations in differential equations.
We begin with a definition. The indefinite integral of a function f of x is the antiderivative of f. That means if you take the integral of f and differentiate it, plug that into the differentiation operator, then what you get back is f. You may think that this means that the integral is really the inverse of the differentiation operator. Well, that's almost true, but not quite. If you reverse the order of operations and first compute the derivative of f, then what will you get when you integrate it? Will you get f back again? Well, not exactly. You may recall there is a constant of integration involved. And indeed, the indefinite integral of f is a class of functions, all equivalent up to a constant. It's fairly easy to write down a list of integrals that we can compute easily. The integral of x to the k we know is x to the k plus 1 over k plus 1, unless k equals -1, in which case you get the log of x. Integrals of sines and cosines are easy enough. Anti-differentiate and watch your minus signs. And, wonderful to tell, the integral of e to the x is, of course, e to the x. Don't forget the constants. That much is simple. Take the antiderivative. On the other hand, there are some functions for which computing an antiderivative is highly non-trivial. Maybe with work, you'll be able to compute an antiderivative for log of x or secant of x. But no matter how hard you try, you are going to have an extremely difficult time finding an antiderivative for something like e to the x squared. We're going to take some time a little bit later in this chapter to go over methods for computing these antiderivatives. For the moment, and for the next couple of lectures, we're going to spend some time answering the question of why. Why do we care about the indefinite integral? One excellent answer to that question is to be found in the subject of differential equations, where a differential equation is simply an algebraic equation on a function x and its derivatives. For example, the simplest differential equation is of the form dx dt equals f of t for some f. This equation has as its solution x, given by the indefinite integral of f with respect to t. Now, what does that mean? How do we interpret it? Well, one natural interpretation for the derivative is as the slope. So the differential equation is telling you something about the slope of the solution curve. It has to match this function, f. Now, of course, we can see the indefinite integral in here. We can see why there is a constant of integration. Because if I translate this solution curve up or down, I am not changing any of the slopes, and it still must be a solution. Thus, solutions to this simple differential equation come in the form of a family, depending upon a constant. These are often called ODEs, which stand for ordinary differential equations. You will see some extraordinary differential equations later in your calculus career. For the moment, let's stick to a basic example and look at gravitation. As you know from your background in physics, when you drop an object, then it is acted on by gravity, which, near the surface of the Earth, is modeled as a constant, g. Now, we can model the behavior of this falling object in terms of its height, x, its velocity, v, and its acceleration, a. All of these are functions of time. Since acceleration is a constant, we can write the simple differential equation dv dt, that is acceleration, equals minus g. Note we put the minus sign in because we orient things so that up is positive, down is negative. Likewise, because we know the relationship between velocity and height, we can write a differential equation for x. Dx dt equals v. Let's solve these one at a time. Both of these are simple differential equations. The first, dv dt equals minus g, has as its solution v, as a function of time, is the indefinite integral of negative g with respect to t. What does this have as its solution? Well, of course, the antiderivative of a constant is just that constant times t, and we have a plus c as our integration constant. What does that plus c really mean? It is really an initial velocity. Did we simply drop the object, or did we toss it at some speed? Well, in this case, if we plug in t equals 0, we see that v at time 0, otherwise known as v naught, is equal to this integration constant. Now, taking that solution for velocity and plugging that into the right-hand side of our second differential equation allows us to solve for the height, x, as the integral of v of t dt. We already know what v of t is, and so we compute the antiderivative to get negative 1/2 g t squared plus v naught t plus another constant of integration. What is that plus c? Well, that is really an initial height, since at time 0, all of the other terms vanish except for the plus c. So we can write that as negative 1/2 g t squared plus v naught t plus x naught. This should be a familiar formula to you from your basic physics. Whether it is or not, it is transparent now why projectiles move in a parabolic shape under the influence of gravity. We have a negative 1/2 g t squared coming from the integral. So far, so good. These simple differential equations have simple solutions in terms of integrals. But what happens when we look at the next simplest class, namely dx dt equals f of x instead of f of t? How do you solve that for x as a function of time? Well, we're going to restrict to the simplest, the canonical differential equation of this form, one that is linear in x. This is a very important differential equation. It is dx dt equals ax, for a constant. We're going to think about this one over and over